Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we will discuss about the free space management of file system implementation. That is the management required to manage all the free spaces that is present and available within that physical structure of the file system. What are the mechanisms to implement this management, like the bit vectors, linked lists, grouping, counting and space maps, which we'll discuss in details. The main concept for the free space management is to reuse the file spaces that for the deleted files and for the new files that is being created. So whenever the new files are created, it may reuse the space for the deleted files if possible. Say for some optical disk which allowed that only once write is possible, then it is not physically possible to reuse the disk space. So whenever it is possible, then we may want to use that space again. So a free space list records all the free space that is available of that particular physical structure. Now these are the disk addresses or the disk blocks that is containing no pointers to a file or a directory. So whenever a new file is created, it requires the free space manager to look for the free spaces within that free space list for the required amount of space. The space is then allocated to the file from the free space list and the space is removed from the free space list. Now when the file is deleted, again that space is added to the free space list to use by another file. But as the name suggests, this type of implementation is not always done by using a list. It is done by many types of implementation. The first implementation we will apply to a free space list is a bit vector. In this type of implementation, each disk block is considered as a bit. Say for instance, an allocation of bit contains a bit of 0 and a free disk block will contain a bit of 1. So we are considering an example of a final 32 bits of the allocated blocks, and now we will see and represent these blocks in bit blocks. So these are the block numbers of the free blocks in a 32-bit system. So how it will be represented as a bit vector? All the free blocks will be represented as 1 and other allocated block is 0. So this representation will be done in this way. For 0 and 1 it is 0. For 2, 3, 4, 5 it is 1. For 6, 7 it is again 0. For 8, 9, 10, 11, 12, 13 it is 1. For 14, 15, 16 it is 0. For 17, 18 it is again 1. From 19 to 24 it is 0. For 25, 26, 27 it is 1. And from 28 to 31 it is 0. So the 32-bit is represented as a bit vector of this one for the allocation of these free blocks. Now the bit vectors become extremely simple to imply the free allocation scheme, as it can readily find the first n bit words and the first n contiguous free blocks that is can be allocated to a file. Say for an instance, if we read the file from here, we can see that the first one is here. So that means that 2 is available and also a chunk of memory that is available as contiguous is 2, 3, 4, 5. So it can be readily out. Now some systems which use the bit manipulations can be effectively used in this purpose. Say for the system which use bit vectors to allocate the system and disk implementation, can each read or the sequentially of these bit vectors to see that which word contain the value of 0. Say for instance, if 0 valued word contains 0, that means they are allocated. And to signify the first one bit, that is the first free bit, so we have to move to the first one bit. So here 2 is the first one bit, that means 2 is free for the file system to be allocated. So the number of blocks is definitely be a part or a factor to calculate the disk block size. So the disk block size now then can be calculated as the number of bits per block multiplied by the first bit size at location plus the offset for the first bit. So this gives us the block number of the first free bit. But we can see that the hardware features is used for the software fortunately. Now, if we can use this bit vector that need to be in the main memory for the implementation of this particular free space list management. Now for smaller files, it is no problem to keep this bit vector in the main memory, but for the larger files, it is not mandatorily to be in the main memory for this bit vector. Say for an instance, when we are talking about an 512 bytes of words within an 1 GB of memory, then we can say that there are 332 KB of the memory which is used for the bit vectors in the 83 of the main memory. Now, if the disk blocks are clustered into 4 groups, then the number can be reduced to 83 KB for storing this bit vector. But if we are considering a disk space of 1 TB with a volume of 256 GB per file, then we can say that it will be 512 MB just for storing the bit vector. So for the larger files, we cannot use this type of implementation as the free space management. So our next implementation is the linked list implementation. In this linked list implementation, we use this as a free list of the blocks that is pointing from one to another. So we are keeping all the free blocks together, that the first block is mentioned in the first position of the free linked list, and then the linked list is pointing to the next free block that is available to it. Obviously, this first block is stored in some special location, that is the first block, or we can say, and the last free block contains a linked list pointer to the null. So we will use this much particular free blocks to allocate in a linked list representation. So the first pointer locates to pointer block 2 and then it will move substantially. So first 2 is free, then 3 is free. So pointer moves from 2 to 3. Next it's moved to 4. Next it's moved to 5. From 5 it's moved to 8. Next to 9. Next it's moved to 10. Now to 11. 12. Then 13. Then 17. 18. Now 25. 26. And finally 27. So the 27 will contain a null pointer to its linked list. So we can see that for the first location, it is moved sequentially to the last free blocks. So this method is not efficient because for each free list traversal, we read to all the free blocks that is available here. But fortunately for the free list traversal, the reading of the disk is not frequent as much as the operating system. So the OS uses that if the file is requiring a free block, so it uses the first block that is kept in the first free list of that particular linked list allocation. So we need not to traverse each block on that free list. The FAT or the file allocation table allocation scheme uses these free blocks or the linked list allocation to incorporate in the allocation algorithm. No other separate method is needed here. The next type of algorithm or the scheme that is used in free space management is grouping. Here, other than storing each disk block as a separate free disk space, we are grouping n blocks into a particular disk place. For say example, 2, 3, 4, 5 are again made in a group of n. So for here, the first n minus 1 blocks are free on this block, and the next block is containing the last word to the starting of the next block, that is containing more n free blocks. So in this way, the disk head skips from moving in the linked list becomes smaller while moving in the grouping scheme. The next scheme we are using is the counting scheme. We know that when we are using a contiguous allocation or an indexed allocation for a sequence or a direct access, we can keep the disk addresses as counting from one again to another. So if you are starting from 2, then 2, 3, 4, 5 are used in allocation together. So whenever the system is allocating a space, it is allocated combinedly and also freed combinedly. So keeping in track of each of the disk block, other than if we keep track of the starting block address and the offset, that is the number or count of the blocks that will be allocated to a particular file system, so it will reduce our free list management. Though the list will require a little more space for storing the disk address as well as the offset, but it will actually become smaller than the linked list because the count is always greater than 1 in most of the cases. So here we will count the number of blocks along with this disk address of the first block, then we will store it into the directory entry as a counting algorithm. This method of tracking of a free list space is similar to the extend method of an indexed allocation. Now we want to store this type of allocation or this type of directory entry in a balance-like tree structure rather than a linked list for better improvement in the lookup, insertion and deletion of the file. The next type of scheme that we will use today is the space maps. In the ZFS systems that is used by a Solaris and both Unix systems can provide a larger quantity for supporting file, directories and even file system. That is ZFS supports a system of file hierarchy. So whenever this type of large file systems are used, it can also reduce a file metadata IO to reduce the system performance. So we need to manage this IO performance. Say for a large file system for managing 1 TB of disk and 1 GB of data, then if we use this bit vector representation in such an implementation, so we can see that the bit vectors are scattered throughout the memory, so thousands of hundreds of blocks needed to be updated for that 1 TB of data. Because the blocks are scattered, so we need to update all the blocks and the bits of all the blocks that are being freed and allocated. So this bit vector representation is not used in this large type of system data implementation. So in ZFS, it rather uses another type of system implementation for free space management that is known as a space map management. It uses a combination of techniques to control the size of the data structures and also to minimize the IO to reduce the number of heads or to manage this data structure. So to implement this, the first step is done by the ZFS is using the meta slabs to divide the sections of a device into manageable chunkable size. Now after the meta slabs are divided, now to allocate free space from this meta slabs, we associate it with a space map. The space map uses a counting based algorithm. Rather than using a balanced structure, we here using a log file system based structure that keeps track of all the block activities that is freeing up allocating in terms of time and also in terms of counting. So when these block activities are recorded in a log-based structures, then a space map that is associated with that particular metaslab can be used to allocate free spaces. So the structure that is indexed by an offset and then the log replace on that particular structure to define that which free spaces are allocated. So here the free spaces will be then allocated to a particular file depending on the number of block activities, and again the log will be updated on that structure that the block is being freed or allocated. So every time the log maintains a type of trees or the balanced trees, that will give us the space maps that is associated with these balanced trees. And Git gives us an accurate representation of the allocated and freed space maps associated with each of the metaslabs. Now the space maps in ZFS also used to condenses by using or compacting the combination of contiguous memory into a single entry. So whenever we want to enter a single entry in the directory, that will move to a chunk of the space maps or metaslabs like a contiguous one. Finally, the free space is in the updated and a disk on a part of the transaction-oriented operations on the ZFS. Now, during the operation of this log-based structure system, ZFS also requests receipts for this particular file allocation, and thus the file allocation represents the free space management, a log plus that particular balance tree or the metaslabs for this space maps allocation. So these are all the schemes that is used in the free space management to allocate and reallocate the free spaces for a particular files to reuse the spaces as much as possible. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.